Hello and welcome back. In the last video, we introduced energy and one of the holy grails of physics. Energy can't be created or destroyed, i.e. it is always conserved. So remember, energy is the ability to do work. And however much energy you have before a process is going to be equal to the amount of energy you have after the process. Always true, never found a single violation of energy conservation. So the types of energies that we looked at last video, kinetic energy, potential energy, and Q stands for heat energy. And then remember that we lumped two of these energies together to define a type of energy called mechanical energy. I should be careful, it's not a different type of energy, it's just the name that we use to keep track of the sum of potential and kinetic energy. So instead of saying the sum of potential and kinetic energies, I can say mechanical energy. The two are synonymous. So the definition of mechanical energy is the sum of potential and kinetic energy. The two different types of potential energy that we talked about or introduced last time, gravitational and springs potential energies, are also summarized here. So this is kind of what we went over last video, and now we're going to really focus in on potential energy. So first of all, the gravitational potential energy. So gravitational. When an object is located in a gravitational field, then it has an energy associated with it called gravitational potential energy. And why do I say that? Well, look, I have this pen elevated in this gravitational field. And when I let go of it, what do I see happen to that pen? I see it fall. I see it drop. I see it increasing the amount of kinetic energy it has as it moves in the gravitational field. So what that means, since energy can't be created or destroyed, then it must have had an energy associated with it being in a gravitational field and elevated with respect to the lowest point it can reach. So gravitational potential energy is associated with where the object is located in the field, and that's where H comes from. So let's say I have an object that is located here at this position right here. So we'll call that position 1, and then we'll call this down here position 2. So here's my object, and let's say that it is stationary. In other words, it's not moving at this location. So this is a cliff, if you will. There it is, okay? So if I let go of this object, let's say I'm standing here on this cliff and I let go of this object such that its initial speed is 0, then this object will fall. And of course, we already know how to assess that. We've been working with free fall already in previous videos, so we understand free fall. But let's look at how we apply potential energy to this situation. So what I would do at this point, if I want to look at the object's potential energy as it moves from one location to another, is I need to pick a reference point. I need to pick a plane along which I say y is going to be equal to 0. And it really does not matter where you choose that plane. I could say that position 2 is where y is equal to 0. I could say a quarter up is where y equals 0. I could say halfway is y equals 0. Or 3/4 up is y equals 0. Or position 1 is y equals 0. It really doesn't matter. And so I'll just go ahead and say this is y equals 0. So now the object initially has a potential energy, PEI. The initial potential energy is going to be equal to the object's mass, and that's our object, so there's m, times the acceleration due to Earth's gravity, because this is on planet Earth, this example we're using, and then times the height it is located with respect to my reference plane. my reference plane here. So this is going to be yi. What is y initial in this case? Well, that's going to be 0 in this case. So I would say initially there is no potential energy associated with the object. Notice that it's not going to matter if instead I chose the lower plane as my y equals 0. So let's say that that's y prime equals 0. And now let's look at the potential energy associated with that plane. So I'm hoping you see this in a different color here. I'm also putting a prime in case you don't. So this is going to be equal to the object's mass times the acceleration due to Earth's gravity times the initial location. But now notice that the initial location is above my reference plane in this case, and let's just define that as an h. So this is going to be mgh. So notice that I have two different values here depending on where I chose my reference plane as to how much initial potential energy I have. So it turns out potential energy is really meaningless. It's really the change in potential energy we're going to find that's meaningful. So let's go ahead and continue on here. The object then falls, and let's say that just a nanometer before it hits the ground, we want to again reference its potential energy, and that would be its final potential energy. So PE final for the object, if I measure with the reference plane being at location 1, the final potential energy is going to be the potential energy it has here. It's going to be mg times this location at position 2 with respect to our reference plane, and so this is going to be minus h. It's minus h below. It's in the negative direction and a magnitude of h. So this is going to be minus mgh. What if instead we're using the reference plane in pink, or point 2 is our reference plane? Then the final potential energy is going to be equal to mg times the height above the reference plane, and that's 0. And so we have no potential energy. So now let's look at the change in the potential energy under both cases. So the change in the potential energy. So first of all, the change in potential energy using the reference plane at position 1 is going to be PE final minus PE initial, and our PE final is minus mgh, and our PE initial is 0. So we come up with minus mgh as the change in the potential energy. Now what about when we use our reference plane down here at the bottom of the cliff? What is the change in the potential energy? Well, again, it's going to be the final potential energy, and I should be putting primes on those, sorry, minus the initial potential energy. It's just in case you don't see the pink distinguished clearly from the yellow. So the final potential energy is 0 minus the initial potential energy, which is mgh. Notice we get exactly the same result. Okay, so it does not matter what reference plane you choose as long as you are consistent with all your measurements with respect to it, and it's really the change in the potential energy that's meaningful. Now notice that as this object falls, that there is only one force that is acting, period, on the object because it's in a state of free fall. And so that one force, of course, is the gravitational force, and the gravitational force is one of those conservative forces we learned about that when it does work, acts to conserve the system's mechanical energy. So that means the sum, since it's the only force doing work, we are in that realm of mechanical energy conservation. So free fall, which is the condition we're looking at right now, mechanical energy is conserved. Okay, so that means that KE initial plus PE initial equals KE final plus PE final. Now, let's rearrange those a little bit so that we can look at how we get the change in the potential energy. So what I'm going to do is move the initial potential energy over to the right side, and I'm going to move the final kinetic energy over to the left side. And when I do that, I'm going to have KE initial minus KE final equals PE final minus PE initial. And then I'm going to factor out a negative sign here, minus, so that I can write this as KE final minus KE initial is equal to delta PE. And of course, you'll recognize this as delta KE. So lastly, we have that the change in the kinetic energy is equal to minus the change in the potential energy, or if you'd rather look at it as minus the change in kinetic energy is equal to the change in potential energy. Doesn't matter which side you put the negative sign on, the equality holds. So when we are in the realm of mechanical energy conservation, then this is true for ME conservation. Okay? Notice something else that's true for mechanical energy conservation, and that is that the net work then, since it's equal to the change in the kinetic energy, the work done by conservative fields can be written as minus the change in the potential energy. Using this equation to substitute KE as minus PE. So little subscript c stands for conservative field, so that would either be the gravitational field or it would be Springs field. Either one, or elastic field. Either one would we could use to calculate work done as the negative of the change in the potential energy. So we release the object. It initially has no kinetic energy at all. As it falls, its potential energy is decreasing, and its kinetic energy is increasing as it's moving faster and faster and faster. And just before it hits the reference point down here at the bottom, we have all kinetic energy and almost no potential energy. And just above, the nanometer above, we have no more potential energy, all kinetic energy. And so the sum of the potential and kinetic energies is the same at all points. I can choose any point along the object's fall and sum the potential and kinetic energies, and I'm going to get the same value as any other point that I pick. So this gives us an idea of how to deal with the gravitational field. And in the next video, what we'll do is look at the elastic field, and then we will start applying these to some problems. So we'll see you next time.